Hello and welcome everyone. This is HOOPS Virtual Training Developing Advanced 3D Workflows. I'm Robert Beyer. I'm the HOOPS Product Marketing Manager here at TechSoft 3D, and I'll be hosting the session today. But my real objective today is to introduce you to Florian Maurice, who will be leading the training session. Florian is one of our consulting engineers here at TechSoft and has been with us for just about 9 years. So you're in very good hands for today's session. Thanks for being here. It should be a good session, and I'll go ahead and pass it along to Florian to get us started.
Thank you very much, Robert. So we're going to start this this training session. Maybe I will just introduce myself quickly, and then I will explain you what we're going to do and what are the objectives of this session. So you might be, for the persons who don't know me, you might be wondering who's this crazy guy who is going to try to teach you a bit of coding today. So I'm Florian Maurice. I am French, based near a town called Lyon in France. And basically, I'm doing a bunch of crazy things like hang gliding, as you could see. But more on the technical background, I am a core visualization game programmer. That's my real background. I've been making a few games in a company called Étrange Libellule in Lyon. So I have a lot of skills regarding C++ and visualization, a little bit less on the web side. So I apologize in advance if you see some inconsistencies. But yeah, well, as you know, we are constantly learning. The second thing you might be interested to know about me is that I'm a cat person. Sorry for the dog persons, but yeah, I prefer cats. I also like to play board games with some friends and family. Another important thing also for you to know is I've got a few hobbies, other hobbies like astronomy, astrophotography. I'm trying to take a few pictures, and that takes some of my nights. I also like to dress up as a pirate and organize some treasure hunt for kids and neighbors. And finally, if I'm trying to define myself right now, I would say I'm a happy dad, and soon to have a second child. So that's really what I'm focusing on right now, besides TechSoft, planning hobbies. So that gives you a small picture about who I am and how I got into TechSoft. And now let's jump into this training session where let's define some objectives for ourselves. These 4 objectives, like learning how to integrate HOOPS Communicator, which is a product part of our web platform, into an Angular application. We also try to learn how to write a custom operator to make use of HOOPS Communicator. Using that, we're going to try to refresh your memories about math that you might have learned during your education, or maybe you're going to learn it today. And I'll give you some hints on where to search for the next things, and learn how to use visual debugging for a concrete example to try to make sure that you code as fast as possible with HOOPS Communicator. We're going to take a concrete example, a use case from that I got involved with. And the topic is virtual instrumentation. As an example, I took an example on the web. It's Dirac from Vibes Technology. The idea is that when you want to perform some simulation or data acquisition using real sensors, right now the cool thing is to be able to map these real data to a virtual representation of it. So you can see on the right side, it's a real part where an engineer has placed some real sensors here, some accelerometers. That's the little cubes you can see here. And this operator is going to hit with a hammer the part at different positions and record the data acquired by the sensors. And in order to have a complete simulation and to set up correctly the experimentation, there is a desktop application where you have the CAD file that represents the part, and also the operator is able to place the sensors and orientate them correctly accordingly to the test he wants to perform. So this is the topic we're going to take today for this training session and try to implement and see if we could reproduce that kind of behavior on using HOOPS Communicator. Okay, so you should have been given some files from Robert, from a mail you got, and what we are going to be doing is to use Visual Studio Code for that. So I am going to open a new Visual Studio Code session, and we're going to start from scratch here. So I'm going to make a new folder. So HOOPS Communicator training, and this is what I will be opening right here in Visual Studio. So now the idea is to start with a basic, a new Angular application. So I gave you some references, and basically to start a new Angular application, I'm going to open the terminal, and here I have already installed Angular CLI on my machine, and also Node.js. These are the prerequisites to be using Angular. And I am going to create a new application. So ng new, let's call it HC, HOOPS Communicator. And I'm gonna run enter, and now it will ask me a few things like, do I want Angular routing? Yes, why not? I'm going to be using simple CSS for my setup. And now I clicked enter, so it's installing some packages. It's going to take a few seconds. It's downloading the package and getting all the necessary dependencies to have Angular working. Yeah, there we go. So when it has finished, it gives you back the hand, and we can verify that everything is working accordingly. So I'm just going to go in the new folder HC that has been created, and to launch the server and to try our application, I'm going to type the command ng-serve, and with -O to be able to open, just to simply open my web viewer at the beginning. So here, yeah, I'm going to be using a different port right now. Yes, because I have something running in parallel. So the first time, it takes a bit of time to build the components, but you will see that afterward, it's very fast to just apply the differences of what you changed live on your page. So it's finished compiling, and it's opening. It's in my browser. So If I open it full page, this is the default page that comes when you install a new Angular application. So Angular is a front end for rapid web development, and you see, like, it has default interactions for interacting, clicking on buttons, listening for events, and has a lot of specific package that you can reuse from the package managers. And what we're going to try to do is to see how to integrate HOOPS Communicator into this application. So I'm going to just let it pair. And let's open the content of what's been created so far. So we have a bunch of configuration files that we won't touch if not necessary. And then we have the source folder where we will find our first index page. Just to show you an example, if I change the title here, then I save my file, it's going to detect directly this change, recompile, and you see that in my browser, we've updated the title automatically. So it's really, you can have this open on a screen, and you type your code, and you can just save, and it reloads automatically, which is quite convenient when you are testing things where you don't need to interact much. It's quite interesting. Then the main code here is based in a component called app component. And the concept of Angular is that you're going to have an HTML template, you're going to have some TypeScript and some CSS, and you're going to create some components and be able to integrate these components into the main view to create your application. So if we go, for example, in the HTML, here they are telling us that we can delete everything and just start from scratch. But maybe before doing that, if I search for HT app, I can create a new div here, a div element, just to say hello world. And you will see that basically it's adding some HTML here at this location. So what I'm going to do instead of deleting everything is right now I'm going to try to integrate our web viewer at this location to show you, because usually our web viewer will need to be integrated into an existing code. So I'm going to start here. So the first step to integrate HOOPS Communicator will be to create a new component. So for that, I will be stopping the server. So I press Ctrl+C in the terminal to stop. And I'm going to type the command ng create. So ng new component viewer. Sorry, generate. There are some shortcuts, but here they are not implemented. So ng generate component viewer. And you will see that in the tree view here, it created a new folder with the name I've been giving, and it automatically created some files for me. So the HTML template, the TypeScript, the TypeScript to perform the automatic testing, and the CSS. So this is where we will be adding our component. And you see that they've put something in default here. So the first thing we're going to do is integrate this component into the app component. So for that, you see that the completion automatically detects this new component. And I'm just adding this tag. And this is where we're going to put the viewer. So now if I restart the server, we'll be able to see the new component and where it should be placed below Hello World. Okay. Yeah, so this is, you see that now there's viewer works. So now we are ready to basically bring in HOOPS Communicator files and include that at this very location. For that, we will take the package that you might have downloaded before, so which is HC solution. And let's put it somewhere convenient, like here. And I'm going to extract it in a subfolder. And what I provided to you here is actually the complete, the end result. And we're going to just pick some files that we need right now, and we're going to recreate some of the existing files you see here. So don't copy everything. When you extract that, you just go into the source directory, and we're going to take some elements that belong to the asset folder. And we're going to copy that into the existing asset folder. For that, the most important thing is the JavaScript and CSS and also TypeScript from HOOPS Communicator that I packed into this folder here. So you're going to have the TypeScript, JavaScript, and CSS, and a sample HTML page. So let's just copy that here in the asset folder. It should be quite fast. And whilst we are here, let's also copy the SCS folder where I pre-converted for you some CAD assets using our converter that you have in the web viewer package. And we will be using them right now. We leave the other things for now, but we might go back to that later. So now in our project, we have HOOPS Communicator files, and we need to include that in the page. And there are different ways to do that in theory. Like normally, you're going to use an NPM, the NPM manager to get an existing package, but HOOPS Communicator is not deployed on NPM right now. So we will not be using that. And also with Angular, you can include some scripts so that they are processed when you distribute and prepare the website for production. But usually it's going to try to optimize your JavaScript. And here, HOOPS Communicator has already some heavily optimized files. And you might run out of memory if you are integrated them like you could do for some other components. So the way to integrate them is actually to use them as an asset and then just to reference it in the main index.html. So here, this is where we're going to be able to add the scripts. We cannot add a script directly into a component for security reasons. So we have to add that in the index.html page. So this is a JavaScript. And here we're going to go into assets, HOOPS Communicator 2021 SP1, JS. And the only one you need to install and to link is the hoops_web_viewer.js. It's enough to actually have HOOPS Communicator integrated and working. So now I'm just going to save that. And it's been recompiled, it's been updated, but there's not the viewer yet because we need to instantiate one and create one. For that, we will add an element here in the viewer. So this is where we want to integrate it. And what we will be doing is create a new div. We're going to give it a name. We're going to give it a class. Be able to apply some CSS after that. So here I'm leaving that as empty right now. Don't put anything into this div. It is quite important if you are using redlining and other tools that come out of the box, because if there's any content in there, right now it shifts all the redlining and you might see a shift between the mouse position and where we are actually rendering things. So keep in mind, try to keep it as simple as possible. Now we will be going into our viewer component, and we need to write a bit of code now to instantiate our viewer and have it working. Angular is generating the DOM for JavaScript, and it has every component has a specific life cycle that you can read a bit more about. And most of the time, you're going to initialize everything you need in this ng-on-init function. But HOOPS Communicator requires the DOM to be existing and be created. So actually, it's not in this very function that we will be using creating the web viewer. It's in the after view init function. So we're going to say we implement this interface. I'm going to implement it. And this is really where we're going to put some code to create the viewer. So we're going to have a class member to just contain that and be able to refer to that. And as you see, the TypeScript was provided for Communicator, so I'm able to use it for code completion. So I'm just creating a viewer member here, and I'm going to be using it and create a new viewer here. So for that, we create a web viewer. And the web viewer requires to have some parameters, so a structure that has some default parameters. It needs to know where to be put. So that's the container ID. And here, if you remember, in the HTML, I created this div with a specific ID, so I'm going to be using that for now. And I can save right now just to see if it has any effect. Not yet. We also need to inform the viewer which model to load. So this is the endpoint URI value. And here we need to put a relative path into the assets folder where we have created some, we've added some SCS files, and we're going to be loading the micro engine SCS for now. Nothing is happening because we have not started the viewer. So now that we have created the viewer, the only thing you need to do is to call start to have it displayed. And here we go. On my page, it's been refreshed, and you see that the micro engine is now visible. Unfortunately, it's not at the location we want it to, and you see that its position is not exactly where it should be. This is something we're going to fix with a few lines of code of CSS. So I have given class to the div where the viewer is placed. So we're going to be able to put a bit of elements here. So let's say we want to have it 100% of the width. Let's say that the height on my machine might work for 500 pixels. Now we want to center it. So let's say left and right 50%. And here it's you'll see I'm using a kind of a CSS hack to be able to center it. So it's working well on Chrome. I've done some tests and it was working well on other browsers, but yeah, feel free to adapt it. Here it's just really based on this very example. And if you add the CSS, now you can see that it pushed everything below it. So we've already inserted it at the location we wanted. And if I show the border, I help a bit more. You see that's really where HOOPS Communicator has been inserted. So now I can interact, and you see where it relates to. Just giving you a bit of time to write that down and have it set up, because that's quite important. Otherwise, your viewer will be at the center, so it's not right. And the next thing we're going to do is I'm going to show you how to activate the axis triad, because we will be using 3D coordinates after that. So it's quite important to know where the orientation of our camera and of our model. For that, there is an existing function, and you might think, let's try to use that right now. So it's in the view. do we get the access triad, and would you enable that? But if you do this, you will see that actually you no longer have the model loaded, and you don't see the access triad. And if you press F12 on Chrome to just go on the console to see if there is any JavaScript error, you will see some errors here. And this is because we are calling this function too early in the life cycle of HOOPS Communicator. We have a callback mechanism to let you know when the view is ready and when the viewer is ready. So we're going to be using that right now to set that up. So for that, we're going to create two functions that will be our callback. And this is where we want to place, for example, the initialization of the access triad. Of course, here it says that the viewer might be null. So we're going to use the TypeScript shortcut here, question mark, just to say that it tests if the viewer is null or not before calling everything else. But we know from the normal workflow that this will be initialized. And here, what we need to do before starting the viewer is to set the callback. And like for the creation of the web viewer, we need to give some parameters. And so here, the object has a scene ready element, and we're going to use the mySceneReady function here. And in order for it to work also, we need to bind, you see that this callback is referring to this, and it's not, actually it's out of the scope of the callback. So for that, in the constructor, what we can do is to bind this to the callback. So you do that by saying this mySceneReady function, bind. And now, as you can see, it loads the model, and when it is ready, the callback is called, and we have the access triad that is visible on screen, and no more any errors. The next step will be that we are going to create our operator. And for that, we will need to register the operator. This is not done at the same callback. So let's create the callback directly because we're going to be using it very soon. But whilst we are there, we're going to do something very similar and leave it empty for now. So my model ready func, we will be adding that in the callbacks. And here, similarly, we need to let this function know about the class itself. And now we should have everything set up when we will want to register our custom operator. Just pausing a bit for you to refer to everything, and especially here, this is not trivial. And you will see there's one element that is missing, is that if I resize the view, you see that the model is stretched and the view is stretched. It's because we have not informed HOOPS Communicator about a resize event. And so this is something you can do with Angular, and you have many ways of doing that. Basically, let's see if we can do that. So in the class, we're going to add an observable. And you see that when I'm adding these elements, it automatically imports them. And now I'm going to be using them after I've initialized everything. So what we are doing here is basically listening to the window resize event, and we're gonna just catch that and inform HOOPS Communicator about it. So now we are getting the event, and what we'll be able to do is pass that to the viewer, saying, hey, this is now that you would need to resize the canvas. So click here. So I'm missing import. What? Okay, it's saying that it's not using my. Okay, I've got a little difference between the code I gave you, and this is because in the code I gave you, I've upgraded from Angular 11 to Angular 12, and they are changing a few things. And for that, I'm not sure. Maybe I should add that directly in the constructor, then fix the error. Yeah, seems to be doing the trick. Let's see. So if I go back to my page, now you see that when I resize, now the model is no longer stretched because we pass the information to HOOPS Communicator so that it can recompute the exact camera, render it. And one thing that is missing and that we often forget is On the description of the component, we need to remove the subscription that we've done. I always forget, so it's something to add. So now we have the basic setup to have HOOPS Communicator integrated into Angular, and we will be able to start coding a custom operator. And for that, what I'll do is just create a new folder. This will be my operator, base sensor. And right away, we're going to also have another file that will represent the sensor. Let's leave that empty for now. And to place the sensor, what I'm going to do is refer to, I'm going to take the code from HOOPS Communicator documentation, just to start from fresh and not re-implement everything. So I'm just going to steal that as a starting point. It will be the best way, but it works. And this is JavaScript. So let's turn that into TypeScript. So I'm going to add export, rename the class. And there the variable. We're also missing part ID. Let's see, should we be using that? No, not really. Why not? Just to test if everything works fine. Assume the part ID is a node ID here, but can also be null. Event is a communicator event. Release that to any. Right. Yeah, so here it's complaining that the part ID might be null, so just so that thing is working, let's just add that temporarily because we're gonna just remove that afterward. But now I made everything compile. I started to have a default operator, custom operator, and we're going to try to register that and see if it works. For this, what we will do is register this operator. I'm going to create a new function here. So we want to do that just if the viewer exists. And as we show in the tutorial, so the good thing to do here is create the operator, and let's see. Yeah. Then we get a handle. Registering it. So that's the necessary steps to register my new operator on the stack. And now what I can do is register this operator in the myModelReady function that we wrote before. We cannot do that before it started. We cannot do that when the scene is ready. It's very important to do that just at this stage. Have it working. So now if I go back to the view, we should have pushed the operator on our stack. And normally here I'm right clicking, and that's the behavior of that was coded in the default example. Like when you right click, we change the transparency of the part that was clicked on. So we have our operator that is working in our view, and we'll be able to just customize it and write our own to reflect on the topic we selected, and build from there. Is there any question, Robert, in between? I think it's a good time to pause before I start into the next part of the training.
Yeah, so far, no questions. Nothing's come in, but please feel free to submit anything that comes to mind. But no, you're good to continue.
Okay, good. So now what we're going to do is actually write a more useful operator for our topic. And what we want to do is to show a part where I move the mouse first. And maybe, yeah, let's see, maybe I'm going to show you the result we are targeting before we implement it. It will give you a bit more context of what will be the next steps. So I'm just running the light version. That's the right one. That's the goal that we are trying to achieve there. So you see that there are some debug functionality to show the bounding box and the size of the model. And you'll see that whenever I move my mouse, there's actually a model that I've loaded and that is interacting. And the idea is to be able to orientate it according to the surface of the model. And that when I click, I'll be placing an instance of it. And you'll see that also in order to place things, we're going to do also some collision detection to prevent overlapping sensors. So that's the idea. That's what we are trying to do and to achieve now. So let's forget about this right now. So just commenting it out. And the first thing we want to do is really just focus on what we will be doing when the mouse moves. And for that, well, it's a bit the same here. We're going to take the config and get the position. And maybe the first thing we'll need to do is also to create the sensor. So we're going to need a few elements. So the part ID, we don't really bother, but we're going to have a review part. Of type sensor, which does not exist yet. So we are going to create that afterward. And in the constructor, review part initialize to null. And if we go to the sensor, what we can just write basic class. So there's a bit of code to have things set up. Now we can leave it to that. So what I'm doing here is writing an initialization function that will load a second SES file in the existing scene. And for that, you have several references in our tutorials or in our documentation or not samples. And let's see what else I need. I'm not sure why the code completion is not happy with that right now. I'll try to do that later on. And we will be using okay, so it's complaining because I'm not importing the store. I'm sorry for that. I'm trying to understand a bit why it's not detecting correctly. Oh yeah, that's why. There we go. Syntax error. Yeah, an obvious thing here, but We can be using that later, but for now we can just do that. We need to return an element if yes, this is empty. It will be when we've already instantiated the sensor and that we just want to clone some other ones. We don't want to reload the same model. So in this case, we're going to return also. And why we're complaining about that? I'm not sure. Let's see why I needed to set that to undefined at some point. So we've created our sensor class, and we're going to try to load that on screen at the beginning. And what we can do here is, you see that this is asynchronous, and it's a bad practice to load, to use an asynchronous function into the constructor. So this is why we are, basically I took all the code out of the constructor, that the code that is using asynchronous code, and I'm going to use that function, create sensor. Okay, yeah, this is why it was continuing, and this is why here. There we go. So we will be able to call the create sensor functionality now. By location. We will be doing the same here. We're going to add an initialization function. this is where we call our function that we created just before. And we pass the second asset. So yes, sensor.scs. So you see that in the SCS files, I gave you a big model called drill, the micro engine that we loaded, and the sensor SCS, which is the sensor that I converted. It contains only one part, and it's important because the code I provided to you is using only is instantiating only one part. If you had a complete assembly, you will need to add a bit of code that is illustrated in one of our tutorial, the additive manufacturing one. That's quite important to mention. We'll see about that later. Okay. So now, instead of instantiating the sensor directly, when I create the operator, here, instead of creating it directly, what I can do is instead call this of course. That means we need to put that as asynchronous. Now, if we go back to our implementation, there we go. So sorry, it took a bit of time to write things correctly. You could hack that by just putting the code to instantiate and load the SCS file in the constructor, but it's not a good practice. And depending on the speed of your computer, you might have some weird behaviors because of that. So what I've shown you is really the way to implement it so that you don't end up into timing issues with the promise. So I'm conscious that we might not go as far as I expected with this tutorial. But so here we have our sample part that we're going to be able to manipulate. So now if we go back to our place sensor, we're going to try to manipulate that and stick it to the mouse. So first thing is to make sure that the event we are getting is handled so that our other operators don't get it, get this event and handle this event, we're really going to burn that. Yeah, one thing that I yeah, I wrote the accessor, so let's write the accessor for the getting the node ID. So and that might be why it was complaining before. I think now I don't need to put that anymore. Oh, maybe I do. Okay, I'm getting this weird error. I'm gonna have to find out why I'm not catching that. Don't know why it's complaining on this version of Angular and not for. Say I give a wrong node ID, it should not have an effect. Yeah, I'm sorry for that. Let's see if I can show you something else when I'm conscious of the time we have left here. And I get it. Yeah, I started to two complex things, so maybe let's try. We won't achieve all the goals we wanted, but let's see. Let's on the few minutes we have left together, so that I can maybe tick one of the boxes that that I've set up as a goal.
Hey, Florian, sorry to interrupt. There is a suggestion in the chat. I don't know
Yeah.
if you've been able to see that.
Florian speaking to Florian. Okay. Yeah, that's correct. Yeah, I'm not sure. Yeah, that would help. Okay. But yeah, thanks for the suggestion, Florian. But yeah, I'm just seeing that we have basically 10 minutes left. So maybe one thing I could illustrate is by taking the existing code and maybe do a walkthrough of it, just on the math concept. So to explain you the theory, because you have all the source code that I was trying to reproduce here. And the idea really is that there are two math concepts that you can use to place and orientate the part and the sensor correctly. And it involves the dot product and the cross product, along with matrix calculation. So let me explain to you what I mean by that. So what we're able to get with HOOPS Communicator is the normal of the selection where the mouse is over. And in order to transform the sensor at the right location, we apply a translation. That would work, but you would have the basically the sensor be oriented always the same way. So to go beyond that, you need to do more and recompute a coordinate system. So recompute a coordinate system. I've got one. There's one other reference. Basically, yeah, to transform a part from its origin or its local origin to another location, we need to compute a 4x4 matrix. And in this, you're going to have the translation, which is easy to get because this is the position of our mouse and where we casted a ray and where we hit the existing part. And we need to recreate basically this coordinate system with the X, Y, and Z axis. The Y axis will be the normal, where we face, where we hit the part. And so we need to recompute this X and Z axis. So to do that, we're going to be using the cross product of the normal and the recomputed axis. There's one caveat where the dot product will be usable, is that this arbitrary coordinate system and this arbitrary axis we pick, for example, we choose that arbitrarily that the up will be the y-axis and that we're going to choose z-axis as the second arbitrary axis. And it will work most of the time, except when these are nearly collinear. So if you are not testing for where the normal is, you would get into trouble in some areas where you get close from the z-axis. So in this case, you will need to you will need to detect this case, and instead of choosing this axis, just opt for the x-axis, which will be relatively far, and you won't have computational errors like you would have and some instabilities. And for that, we are using the dot product. The dot product is a cool feature, and I think I wrote a little sample to illustrate that interactively. So if you go on /dot when you're going to build a complete example, you're going to have this, and it's an operator where I'm just illustrating one vector, one arbitrary vector, and the other one that I'm manipulating right now. And you see the dot product here is a simple scalar value, which has the interesting property to be the value, the scalar value of the projection of this vector on the other one. And when these are unit vectors, it's quite cool because you have some interesting properties. Like if they are nearly collinear, then the dot product is equal to 1. If they are in the opposite direction, then the dot product is negative. So what you can do is really use that. It's very fast and efficient to compute. And this is what I'm doing here. Like instead of I'm testing if my normal is nearly collinear to the z-axis. And in this case, I just swap, and the chosen axis I'm going to use to recompute my coordinate system will be the y-axis. And then yes, for debugging, you will see that I was using the line markups, and I've been deactivating them in the end to render the bounding box in this in the final sample. But if you don't render the bounding boxes, you can just reactivate this, and you will see the lines normally the normal rendered and the coordinate system rendered. Okay, I see that we are running out of time, so maybe it's time to wrap up and see if there's a few questions before we stop there. Maybe let's see a recap of the calls we had today and see what we've been able to achieve and what not. So we wanted to learn the basics to integrate our viewer into Angular. I think this objective has been achieved. Of course, we could go deeper, and maybe this is what took too much time compared to what I was expecting. Learn how to write a custom operator. I don't think we achieved completely this objective, to be honest. Yeah, the operator I chose takes a bit of time to write it correctly. I hope I put you on the right track and you have the code sample of what we were trying to achieve to refer to. And you can also contact me directly using the email address that you will see right after. So this one is partially achieved. Refresh, learn a bit of math. I guess we've done that in less than 5 minutes. It might have been beneficial to see a bit more. I wanted to show you, how to use the matrices to do the proper transformation, to place the part. So we barely touched on that, and yeah, this objective we've not achieved, unfortunately. Yeah, thanks, Robert. I see you've put my email address on the chat window. So yeah, hopefully you learned a bit out of this session. We'll see if we do another session or record it offline, so you can refer to it where I go through the material to provide that to you. And yeah, if there are any questions. We have a bit of time left.
Yeah, thanks for that, Florian. That was great. As Florian said, there's his email addresses in the chat. You can access that and reach out with any questions. Feel free to submit any questions you do have in the next few minutes. Other than that, we can wrap things up. We'll provide the recording as soon as possible. So I'd say by the end of the week, we should have the recording session out to everyone. So you can revisit that if need be. I don't see any questions coming through, but thanks again, Florian, for walking us through everything today. That was excellent. Thanks everyone for attending and following along. If you're interested in future trainings, you can find them on our website, also in our newsletter, the Hoops Scene. We'll talk about any upcoming training sessions we have in the next few months. But other than that, thanks again for joining, Florian. Thanks again, and we'll talk to everybody soon. All right, bye everyone. Thanks.
Bye.
Hello and welcome to the next steps of this training regarding advanced 3D workflows. We left off with an Angular implementation where we integrated our viewer, our web viewer, and we started to create a custom operator. This custom operator, right now we have added another SCS file that we load into the scene and that you can see here in the 3D environment. And we want to place this sensor on top of the 3D element. So the first step is we want it to follow the mouse. So this is what we will be focusing on. And we want it to be placed exactly at the right location when we go over an element. So what I created since the other video is I've just prepared an update function in the sensor. So here all the code we're going to write will be located in the on mouse move and in the sensor product. All the part here that is highlighted is to perform the selection only on the face of the CAD model. And when we get this element, the interesting thing is we can grab some information about the selection itself. So for example, here when we get the face entity, you can see that we can get the position and the normal. These are the two elements we're going to make use of to implement our custom operator. So we grab the position where we select the entity, and what we can do with this is create a translation matrix. So this is the position matrix. And we're gonna apply this to the sensor. So you see here that I created a public element for speed, where we assign this new position and we will update the part. So you see that for the update, the only thing we do right now is to set the node matrix to the appropriate node of the sensor. So if we save, now you see that it's still not moving. There's one missing element. If you remember, when we initialize the sensor, we load an SCS file using load subtree from SCS file. And what it returns is a set of nodes. As this is a simple part, there will be just one node. So here we take the shortcut and we assign the node ID, the first node to the node ID. So now we save and go back. And now you see that when I hover the CAD model, then the part is following the mouse. But the strange thing here, the strange behavior is that the part is following even when we are outside the CAD model. And the reason is that the ray picking is actually hitting the sensor itself and returning the hit point on the sensor. This is not really what we want, so we need to find a way to remove the sensor from this preview part to be picked. And you see here right now that it seems it's not placed right at the right location over the part because of that. So what we're going to be using is these instance modifiers. You see that there's many of them, and the one we want to use is to not select on the node ID that corresponds to the sensor. Now you see a difference in the behavior. The part seems half inside the model. So this is wanted. That means that really now the intersection point we are getting from the ray is really with the CAD model. And we translate the part correctly, and when I move outside the CAD model, then our operator no longer updates the part. So that's correct. So the next thing we want to do is to update the rotation and the orientation of the part correctly. And one thing that's going to help us also is to make the part semi-transparent. It will help us after with our debug session. So we set the node opacity to 50%. So now the part is semi-transparent, and this will help us to see a bit more where the hit and how to place the part correctly and make sure that we have the good values. So now you see that for the flat surface here, the position is correct, but when I go on the rounded surfaces, the part is not oriented correctly. We will need to basically take the normal and create a new coordinate system to orientate the part correctly on the CAD model. For that, we're going to go back to our onMouse move function, and from the selection, we will get the normal information corresponding to the face that was hit by the mouse. What we will do first is maybe to output the line visually. For that, we will create a line markup, and this line markup, we will need 2 points to create it. The first point will be the position where we hit the model. And the second one is the position that we make a copy of, and we add simply the normal vector that we got back. The thing that is left now is to display this line normal. We will provide a color, a specific color to it, and as it will be the z-axis, we will match it to the blue color. You will see it will help us with the comparing to the axis triad. So if you go back to the model right now, you don't see it yet. So it's also necessary to add this line normal to the line manager. Now, if we test back our operator, well, you see there's something here, a blue line that is created, and it corresponds to the normal of our part. But you see here, it's creating many normal lines, which could be quite a mess. So one thing that is left to do is to remove every line when we move the mouse. So at the beginning of our on mouse move, we will just delete all the lines. Now you can see that we managed to create a visual debugging tool very quickly with our line manager, which is not meant to provide this functionality, but it's a good way to hack the existing tools into HOOPS Communicator, just to make sure that you speed up your development, because all these 3D calculations need to be right. Now we need to compute the two other coordinates in order to create our new coordinate system for the transformation. So arbitrarily, we're going to take two axes, the y-axis and the z-axis, and the default one would be the z-axis. From that, we're going to create the x-axis of our own coordinate system. And for that, we're going to use the cross product. The cross product is an operation that permits to create a third vector that is, if you want, perpendicular to the two other axes that we chose. So here we're going to do the cross product between the chosen axis and our normal vector. And similarly to our line normal, we will just create a new line and add it so that we can make sure that we compute the right element. So we start from the position and we just add the cross x vector that we just computed, and we set its color to red. And let's verify how it looks. Okay, so we can see that we see a red line, a red vector that's getting generated. And you see that it's following, the computation seems quite good, except when we get closer to the z-axis, which is here in blue, because the cross product of two collinear vectors is the null vector. So we're going to have to handle the case when we are very close to the z-axis, and we will have to pick another axis for that. So this is the thing we're going to check a bit later. Another thing that you see is that the red vector here has its size that changes. And this is because the cross product does not give a unit vector in the end. So if your axes are not really unit vector themselves, then you can have some issues with the magnitude of the vector. So here we normalize the result, the cross product, and you see that we are getting an axis that is a bit better independent of the orientation. But we still have the issue when the surface is pointing toward the z-axis. So to bypass that, we will need to test to find a way to detect this special scenario and to switch to the y-axis in this case. And this is the great property of the dot product that I showed you in the previous video. If you remember, when two vectors are collinear in the same direction or in the opposite direction, the specific property of the dot product is that the value is equal to 1. So here what we will do is verify if our normal is nearly collinear to the z-axis. For this, we're going to use an approximation, say 0.99. And in this case, we need to change the axis that will be chosen and pick the y-axis. And by just doing that, it should fix the issue we had. So have a look at the red arrow. Now it's getting computed correctly, even for the flat surface here that is pointing toward the z direction. And we can also verify that the behavior for the surface below, and this is the case where when it's pointing directly in the opposite direction of the z-axis. And you see here that there's a flip, a quick flip of the x-axis. And that's really up to you to decide how you want to handle that. For this specific demonstration and operator, it's totally fine, but maybe you want to elaborate on the logic on how your operator should behave in this case. For us, we're going to stick to that. That's perfect. So we have two axes, and now we need to compute the y-axis. To do so, we're going to do the same. We're going to apply the cross product of the resulting cross x that we computed and the normal to regenerate a good orthonormal coordinate system. And we will output it in green also with our debug tool here, just to make sure we have a good coordinate system. And you see that the coordinate system we have here is similar to the axis triad that is displayed here on the left. That means that from there, it seems we have the three basis axes to be able to recompute a new transformation, which will be the rotation to orientate the part correctly. So for this, we create an identity matrix, a rotation matrix, and we will use the three component vectors, so cross x, cross y, and the normal, to recreate this rotation matrix. So similarly to the translation matrix in our sensor, we're going to create a rotation matrix member, just so that we can store that. Of course, this one does not exist yet, so let's create it in our sensor. And the thing that is left for us to do is that we need to take that into account now in our update function of the preview part. So previously we were just setting the translation matrix. Now we need to compute the resulting matrix to apply, and this will be the multiplication of the rotation matrix followed by the translation matrix. So we create a temporary matrix which is assigned to identity. We then multiply this identity matrix to the rotation matrix, which basically results into the rotation matrix. And we also multiply it by the translation matrix. And now we can provide that to this resulting matrix, and we should test. Now you can see that our preview part is also following this coordinate system and is oriented correctly on the CAD model. You can test quickly the different type of surfaces to make sure there's no special case we would need to handle. We now have our preview sensor, and what the next thing we want to do is to place an existing sensor on the model when we click on the left mouse button. For this, we will work on the on mouse up event, and the first thing we need to do is to catch everything. So what we will do here is make sure there is a selection and that the current button being up is the button left, to make sure that the event is not propagated to other operators. We set the event to handled, and now we'll be able to place the instance. So for this, we take the shortcut of the model. And the first thing we're going to do is to grab the net matrix of the preview part. Okay, here I see that we need to check the preview part is existing. What we will do also is, instead of adding directly the model here, we're going to create a new node. And here we could place a matrix directly, but we will not. So this node will really just behave as a container. So we don't provide any matrix to this node. Now what we do is we get the mesh IDs that belong to the preview part, and for each of them we're going to create a new element. So here. So it's a bit challenging with all the promise system to find out our way. Here I think I'm missing some brackets. Here we are. So for every mesh ID, we create a new instance mesh data that we color green. And for now, we don't do anything with it. Let's see the results. So now when I release the mouse, it's creating the mesh, and you see that we can hit it, so that's not something we want. And they are created all at the same location because we have not yet applied the matrix. So the first thing we want to do here is to remove the selection possibility. So do not select. And the second thing we will do is to basically create a sensor. So right now we want to reuse the existing SCS file that has been loaded, so we just provide an empty string, but we provide the existing ID that we just got because we've created the mesh, a mesh instance, and we provide that to our sensor. And we will just place the matrix on the container. Let's see if that's enough. Yes, so now you see that our preview is right at the good location, and we can create and add some sensors, and you see that there is no hitbox for the sensor, so we can place them wherever we want. One thing left to make sure that everything is all right and in synchronization with our sensor, we're just going to update it right here. But now basically we have a way to create and place some sensors on our CAD model. The next thing we can try to do is maybe to perform some collision check to make sure that we don't permit these kind of use cases where two sensors would overlap. For this, we will need to keep a track of all the sensors that we have created. So when we create a new sensor, we're going to add it to a list of sensors, and it's just a simple array that we will create. So we will declare it and initialize it in our constructor. So now every sensor that I add will be in this list of sensors. And this is where I will be introducing the helper class that is in the package, which is the Orientate bounding box. So if we go back to our solution that I provided to you, if we go into the assets, you see that we have some helpers here, and we're going to get the OBB. So I'm just going to copy these assets here in our asset folder of our current solution. And this Oriented bounding box will be attached to our sensor. So we will update the sensor accordingly. But before this, let me show you what the Oriented bounding box class helper can do. And for that, what we will do is we will use it for the main model also. So when we go back to the viewer component .ts, we have our my model ready function, and that's when the structure is ready. So right after we activate the operator, we're going to add an OBB So here I'm getting the root node of the model. I'm gonna ask to compute the existing bounding box from the viewer. And here you have different options. So we want to ignore what's visible. We don't want to include the excluded elements, if any, and we want a tight bounding. And here you see it's an asynchronous event. So here we have to transform this to an async function. And now we have all the elements to create a new OBB element. So we provide the box, the bounding box that we just computed. The matrix, well, let's leave it as an identity 1. And now the thing we can do also is to register this OBB with the markups, because I provided also some debug information with that. Here we see a little issue with, it says it can be undefined. So let's see if we can work around that. Go. And I see that with Angular 12 they have a new validator for TypeScript, and so the code I provided, the helper I provided to you, might not build directly. You could see the error here. So let's fix this quickly, like just inferring the parameters. So it's good, this new this new TypeScript validator is well, more restrictive, but it permits you to avoid some errors. So here I've just updated to provide a type, and now that should build. And you could see, so maybe it was too subtle. If I just refresh the page, you see at the beginning here, you now have a displayed bounding box in red for the global model, plus some markups to show the three main dimensions of this box. And so this is part of the code that is in the obb.ts file that is just used for debugging purpose. But it's I think it's cool for you to have a reference to it. And it makes use of real 3D lines, contrary to the bounding box samples that we provide, where it's SVG element. So that means that all the lines are above the model. Here you can see that the red lines that are behind the model are not visible. So it's really 3D lines in the model. And here the problem you will see is that as soon as I hit the CAD model, so here if I rotate everything is fine, but as soon as I hit the CAD model, the lines disappear. And this is because of our debugging elements here, the coordinate system that you see attached to the element, because we remove all the lines from the line manager. So what I will do is go back to our place sensor, and on mouse move we will just remove this, as now we are satisfied with the transformation here. And we can also remove the creation of the lines here for debug purpose. Save back. Okay, and now when I mouse over, my OBB elements are no longer removed. So that's one of the things that the OBB element provides. So let's try to attach this one OBB item to every sensor that we create here, and it will enable us to do some collision detection based on these bounding boxes. For this, there are three main elements that we need to add. As you could see when I created the bounding box for the main model. And these are, well, first the OBB. So let's just import it to have it working. When we register the element, and because we want to be able to remove it, we also have to get and store the OBB string that we get back. And the additional element we need is also the original bounding box of the sensor when it's loaded, so that we can provide the initial state without any transformation. So what we will do is use these and just when we update the matrix. So below our update, so let's forget about that right now. So we create a new OBB. So it will need the original bounding box, the net matrix. So this is something we need to compute at some point. And of course the viewer. So the net matrix is something we're going to compute here. And basically we will just compute it after everything. So here we set the node matrix, and we're going to compute the net matrix. So this is the resulting information. So it's the local matrix of this sensor plus all the possible transformation that would be from the root to this sensor. So that's what we call the net matrix. The other thing we need to do to display it, we need to register the OBB. And for that, we just use the markup manager. And we register the OBB, and in between we just get the string here to be able to delete it. You can see one thing that we did not do already is to assign the original bounding box, and this can be done during the init. So during the init function, you see that we call this underscore initialize function just to make sure we don't duplicate the state, because we will need to compute this box in any scenario, like when at the first load of the original SCS file, but also when we create it from an existing one. So here we're going to use get nodes bounding, and we provide the node ID. And the second parameter is something a bit special. So it's a structure, and you see that we can say type bounding true, which is quite important, otherwise it might not compute the right one. And all the other ones we don't really care about, but it's necessary to mention them. So there we go. Now the original bounding box is this one. And we can call update also here to make sure that everything is synchronized and that we register the bounding box as soon as possible. So we are still having some issues there. Okay, so they want some default values, so and here it will complain that we cannot assign nulls, so what we can do is just create a fake one. That will be replaced later. And let's see if we can do the same. Here, yes. Now it compiles, and so now you see that we are creating a bounding box every time we move. So we are missing the piece of code to remove the existing markup each time we create a new one. So let's try to fix this, and this will be in our sensor when we update. There's one thing we want to do. And it's removing the lines. So it's a bit of code I wrote because we don't know when the bounding box is destroyed completely. So the first thing is to remove all the lines that were supplementary, and you see that now we just have the new lines that are created, and now there's also the markups that we need to remove. So we need to ask the markup manager to unregister the current OBB string. So that was the previous one, and because we're gonna create a new one here, so we need to unregister it so that it's not displayed anymore. Now you can see that we have an operator where we have a bounding box, an oriented bounding box for our preview sensor, and we also have a preview bounding box for the sensors that I place, but not yet the collision detection between them. This is the thing we're going to add right now. For this, we need to implement a collision function in our sensor. So I'm going to type it because it's quite interesting to show you how it works. So we're going to be provided another sensor, and we're just going to return a Boolean. So our own OBB has a function called collide, and what we do is we just provide the other OBB of the sensor we are testing. So if there is a collision, we return true, otherwise we return false. Now we need to see where we're going to use this collide function, and I think an appropriate place might be when we do the update. So we update the part, and then we're going to do the collision detection. So there's a bit of code here, so we're gonna just put it in another function that we will create right here. And let's just win some time. I'm just gonna copy paste that, and just encapsulate everything here. So here we just there's a bit of code just to highlight and color the items correctly. So when there is no collision, we want to render it in blue, and when there is collision, we want to render it in red. So that's the bit of code that we add here. So basically, every time we reset it to the blue color, and we're gonna use this collision, just when there is a collision, we're gonna highlight it in red. So let's see if it works directly. So you see now our preview part is colored in blue, And if I add a part here, yeah, when I get close to it and there is a collision, we highlight our preview in red. So right now we don't do anything to prevent it to be added, but that's some code logic you can add later. And here the collision detection I implemented for you is using the SAT algorithm, which works well on convex objects, arbitrary convex objects. And here it has been optimized for bounding boxes to speed up the code. And this is something you can reuse directly if you have these simple shapes, but it will not work for complex shapes. It might not be fast enough due to my implementation, and it will not work for concave objects. So it's really just an approximation between bounding boxes, which is enough for most of the cases. If you have a look on the existing code that I provided to you, you will see a bit of extra logic that I have added, like being able to rotate the sensor using key inputs. So I invite you to have a look on the onKeyUp event just to see how this can be done. It involves that I have to keep a local rotation element when I do the matrix computation for the sensor. So it adds a bit of logic here. You also have to make sure that you register for the input, and this is done when you initialize the structure here. You have to call this function to make sure that you capture the key inputs when you are in the web viewer. And I think, yeah, we will wrap up this training session here. I invite you to have a look at the code more deeply, and if you have any question, please feel free to contact us via my email address, florian@techsoft3d.com, or contact our support if I don't provide any answer by then. I hope you enjoyed this video and that you learned some elements here that will help you in your existing project or for a future project using HOOPS Communicator. And see you next time, hopefully for a future training.